Welcome to this paper, where we will be exploring when agents should explore in a reinforcement learning setting. This paper is going to be a bit less quantitative than some of the other reviews that I've done, and a bit more qualitative instead. So we're going to be discussing when agents can explore, what triggers to use to begin and finish exploration, and things of that sort. So in order to begin this, I want to draw some parallels to the realm of biology and essentially what we can see in animals, how they explore and what they do, even as they become sort of masters of their crafts. So exploration is about the balance between taking the familiar choice that is known to be rewarding and learning about unfamiliar options, which could be more valuable than the familiar ones. So even if you've sort of refined your strategy to doing a particular task, it might be that you've missed out on something. And so even after you learned something, you might want to keep exploring. And of course, during the process of learning, you also want to explore because it's quite likely that the solution you're currently pursuing is not the optimal one. There's been research on bees, essentially studying how they conduct their foraging excursions, and they've considered trade-off dynamics between visiting and exploiting flowers that are close to the nest, so they would be very easy to essentially harvest, searching for new flowers and resources, and exploiting learned flower visitation sequences. And what's remarkable or interesting about this research is that they found that experienced bees combine these behavioral strategies even after they find an optimal route that minimizes travel distance between flowers. So let's imagine you are a bee, you've learned this particular sequence, it seems to perform well, and it's sort of doing its thing. But even then, and even in such a simplistic creature as a bee, you would see exploring behaviors where they regularly investigate other courses of action to see if potentially that can bring more utility. And this paper focuses on when to explore, expanding the class of exploratory behaviors beyond the commonly used monolithic ones. So what we say what we mean when we say monolithic is essentially epsilon greedy, and the sort of standard framework that one tends to apply if you don't think too much about the way in which you want to explore. Okay, so to kick this off, the actual theoretical material of this paper, we first want to discuss different exploration periods. So there are a number of different sequences and also combinations that you can use to essentially construct how your agent is going to explore. The first one, and perhaps most commonly used one, at least in sort of crude reinforcement learning approaches, would be a step level exploration period. So that essentially means that on a step level, so every step you have some perhaps probabilistic framework for when you would explore or when you would follow essentially the best action. So it's taken independently at each step, affecting one action and one action only. And the most common example here is the epsilon greedy algorithm, where in every step you have a probability epsilon that you're going to explore, in which you would most likely take a random action from, let's say, uniformly distributed from all of the actions that you could potentially take. And in the 1 minus epsilon case, which is the most probable case, you would simply stick to whichever strategy seems to be the best one according to what you've learned so far. There are other ways you could explore though. So one example here would be experiment level. So that would mean that all behavior in training comes from explore mode and learning is off policy. We're going to see an example of this in the next slide to make it a bit more concrete what we actually mean when we say experiment level. This third example we have is episode level. So the mode is then fixed for an entire episode at a time. For example, training versus tournament in a sport. So in the training mode or during the training episode, you would then stick to exploratory behavior. And in the competition mode, you would then use your, let's say, best course of action according to what you've learned so far. The new or sort of additional way of exploring that we are introducing in this paper is the intra-episodic exploration period. So that is essentially in between step and episode level exploration. It's sort of undefined exactly, or well, the constraints on when to explore are less rigorously defined than in, for example, step level, but it's essentially everything in between. So it's introducing the full range of complexity in how we could potentially explore. So to give a graphical example of this, we can look at the following graph. In this one, we have a number of different illustrations of periods here that the agent is sort of interacting with. We have a full course of the experiment, which is the entire length of this bar. Then we have these sequences here, which are episode boundaries. So that would be, for example, training, tournament, so forth. Then we have different modes indicated here. So pink here always indicates explore mode, and blue always indicates exploit mode. And what we're trying to do is illustrate the different periods that you could potentially make use of in this kind of setting. The first one that we see up here is experiment level. So in this case, experiment level with explore mode. So for the entire experiment here, we're running an explore sequence. That would probably lead to a lot of investigation and perhaps acquiring quite a bit of knowledge about the environment, but it's never really exploiting what is learned so far. And that can also be a drawback, because if you're always taking random moves, like let's say you take a uniformly distributed action according to all available actions at every step, you're not really going to compound your steps to get to the parts of the environment that you would get to if you follow an optimal policy. So it might actually be that you suffer in exploration in the regions that make the most sense. The second one we have is an episode level one, so on the second row here, and there we can see that we switch from explore mode here to exploit mode, and then switch back to explore mode. This is, another version of behavior where you would then, iterate between the two, and the boundaries are very fixed, right? They're very clearly defined that this is where we do one thing and here's where we do another. The third one is a step level, and this is perhaps the most common one that you tend to see in reinforcement learning applications, is where you have an exploit mode most of the time, and then on individual steps you have an exploratory action that you perform, and you can see that by these tiny ranges of pink essentially during or across this bar. The ones that we have at the bottom here then are different versions of intra-episodic exploration. So in intra-episodic exploration, we're somewhere in between. We're not sticking to, for example, a full episode mode or experiment level, but neither are we limiting ourselves to step level exploration. We have some sort of sequences of exploration. It's not parameterized by the exploration period name, how long the sequence is going to be. It's not specified where it's going to start. It's not specified where it's going to end. All of those are flexible parts of this intra-episodic level class that we can further explore, and which hasn't really been explored that much in different reinforcement learning applications. So that's what they're taking a first stab at in this paper. Now that we've seen some different periods in which you can group your exploration, we want to look at switching mechanisms between these two. So imagine that you are in this intra-episodic case. You need some way to know, how do we switch from exploit mode to explore mode? And then also, how do we switch back from explore mode to exploit mode? There are different ways of various sophistication that you could do this, and they highlight a couple of examples that they further investigate in this paper. The first version is what's called blind switching. This is the most crude approach for a switching mechanism, and it does not take the state into account at all. So it's only concerned with switching at a desired time resolution. That could either be a fixed number of steps, or it could be, let's say, a probabilistic switching probability. So it could either be deterministic or probabilistic. And if we look here, a deterministic one would, for example, be what we can see here. We have a fixed range of time in between every switch, and it doesn't seem to be, it's not, there's no flexibility in terms of when we actually begin and end. It's predefined. If we look at, for example, this row here, we have an example of a probabilistic switching framework. So we can see that we start episodes and after various sequences of exploit mode, and we also finish them at, after, or we don't run them for the same amount of time. We can switch after a couple of steps, or we switch after a large sequence of steps. It varies. The second one that we have is informed switching, and this is a bit more sophisticated. It tries to look at what the agent knows itself, and it switches its state based on information from the agent's internal state. The specifics of how this works is that the agent has a scalar trigger signal, which is tied to the uncertainty of a state. So if a state is already very well known, the proxy signal would be low, and you would have a low probability of switching if it's probabilistic. You could also define a threshold. So if your signal exceeds that threshold, then you would switch, in which case, it would be deterministic. But nevertheless, a binary switching decision is taken based on the trigger signal. So if you have very high uncertainty in a particular state, it's likely that you will go into explore mode once you reach that state. That's the general idea. The last sort of parameter, or the last thing we have flexibility over here that they're raising in the paper, is the starting mode. So you could either start in explore mode or exploit mode. And if the periods at which you run, for example, your game or whatever it is you're training your agent to perform in, if they are very long, then this can have a significant impact because it tends to have effects on how the agent performs over time, which is something we will see throughout the course of this paper. So if you start with exploit mode, it can be beneficial since early states have often been visited many times. So you don't want to explore in the states you already know, right? So if you start an exploit and you already have a sort of knowledge of the early environment, then that might be a preferable approach because you don't necessarily waste time then exploring the early states as much. However, in other domains, early actions may disproportionately determine the available future paths. In a domain like that, it would be very important to explore a lot in the early stages of the game or the interaction between the agent and the environment for it to learn to take the appropriate actions early in the game. So it's difficult to say which one of these would be better. And it seems to be something which is very dependent on what kind of problem you're considering. Okay, here we have an example then of different exploration triggers and how they perform. So we have a blind step-based trigger to the left here. We can see very clearly defined, switching domains here. So we go for 100 steps, then we switch for a few exploratory steps, and then we switch back to the exploit mode. And we do this continuously until the episode terminates. In contrast, here we have examples of informed trigger signal switches. And you can see that the point in time in which we actually start to explore varies. And also the length of these sequences. If you look here, for example, you can see that it varies across the different exploration periods. And as an example on Graphical, which is where they illustrated this behavior, we can see superior performance for the informed exploration trigger. And overall in this paper, they find that the informed exploration trigger tends to provide utility compared to the uniform one. And that kind of makes intuitive sense, at least, because if you have an agent that starts exploring whenever things become uncertain, it's likely that that would learn more effectively about the environment compared to something that just explores at random at whichever time step it just happens to do so. Okay, in addition to when we explore, we also need to consider how we explore when we're actually in the explore mode. This paper is not too concerned with different ways of selecting actions when we're exploring, but they're raising two different ways that we could choose our actions when we're in explore mode. The first one is what's called uniform explore mode. And this is perhaps the most common one in different applications. It's simply selecting naively a random action given a uniform distribution across the available actions at every step when you're in explore mode. So let's say a very simple example, you have an agent that can go up, left, right, or down. When you're in explore mode, it's the probability is 25% to take either of those actions. That would be an example of uniform explore mode. In contrast to that, they investigate something called R&D intrinsic reward explore mode. The source of that, the paper which lays the foundation for that kind of explore mode is a separate one. I will link that in the description, so please have a look for that. What it does is essentially measures how hard it is to predict the output of a fixed random neural network on visited states. This also becomes a proxy similar to the trigger signals we discussed before on how uncertain a given state is. But instead of just a state like we discussed before, this is more like a state action pair. So given that you're in a state, you evaluate how uncertain would it be if you take an action to go towards a certain state. And given that information, if you have a very uncertain state, that would be favored, and you will therefore be more likely to explore that region. So that's how they work differently. The first example of uniform exploration simply picks an action at random, uniformly distributed. And for the second one, you pick an action that seems to be the most uncertain. There are some minor remarks on the way R&D picks these kinds of exploration steps. to circumvent things like the issues you tend to see with, for example, TV monitors in games where there's always new information being displayed and the agent tends to get stuck in environments like that because it's always unknown. So there are some, additional remarks, but if you want to see the details of that, I would advise you to check out that other paper, which I will link in the description. Okay. Another alternative that they're raising in this paper that we won't really go into details of, but just to illustrate some of the nuances that we have when it comes to these exploration modes, they also discuss software explore exploit modes. So that would essentially be that, or they're raising the point that you don't always have to do, let's say, epsilon greedy exploration where you fully utilize your greedy strategy when you're in explore mode and fully utilize your let's say uniform random selection strategy when you're in exploit mode. You could also have some sort of interplay between the two where you sometimes take exploratory actions even when you're in exploit mode and sometimes take greedy actions when you're in explore mode. You could parameterize that in whichever way you choose. So they have two different values here of epsilon for that kind of framework. So that's another way you could do it. And of course, there are infinite variations of ways you could do this, but these are the ones that are being investigated in this paper. So these are the ones that we will stick to for now. Now that we discussed a lot of the underlying theoretical foundations, let's have a look at the results as well. The first result we're going to have a look at is for uniform exploration. So for all of the different lines that you can see in these graphs, we have uniform exploration, and it's a question of how we switch between the different modes. In the first one, the purple one here that you can see have quite poor performance, it's experiment level exploration. The X at the end here indicates that we're starting in explore mode. That is in contrast to the G that we can see on the blue one, which starts in the greedy mode. So that's the only difference between the two of those, but they're both experiment level, meaning that we don't switch the behavior throughout the experiment. And we can see that the performance compared to the other evaluations here are quite poor, as we would expect from these, because we don't really switch between exploration and exploitation at all. So that's sort of standard knowledge at this stage within the current domain. The next one that we have is this one. It's a step level epsilon greedy exploration. So you would take then with probability 0.01 at each step, essentially you would evaluate the chance of exploring. And if you do, you would take some uniform step according to that exploration strategy. And the two last ones, namely the orange and red graphs that we can see, are for episode level and intra-episode level respectively. The intra-episode level is also informed. So the trigger is informed for this one, and it started in explore mode, which is perhaps less important to note than for these one, because here the explore versus exploit mode really makes a big difference. What we can see from these is that overall, the episode level and intra-episodic level tend to vastly outperform the experiment level ones, which is, as we said, what we would expect. Additionally, at least the intra-episodic one gets the best performance on both of these. So already in the uniform exploration mode, we can see a preference for XU intra here. As we move on to the intrinsic reward exploration, we see a similar story. So again, we see that the two best performing ones are the episode level and intra-episode level agents. These are equivalent to what we saw last time, the essential difference being that the exploration is now informed compared to before. And so we improve over both step level and episode level baselines. And this is the first major result that they're presenting, showing the utility of intra-episodic exploration. So there seems to be some real benefit in doing this. It's not just additional parameterization and additional complexity without actual utility, but they can actually bring some results to the table with this new kind of exploration. The second topic we want to introduce now is self-regulation enhancements that we can make to these models without additional burden. It's actually something that was already used here, but I refrained from presenting it just to give some results before going through all of the different aspects that they're considering. The first of these, so the general aim here is to make the framework better and more adaptable without introducing more hyperparameters, because as you add hyperparameters, the number of combinations that you could potentially create exponentially grows, and it's not a good state if you get too many. So what they're introducing are two enhancements. The first one is banded adaptation. It allows for dynamic adaptation of when to enter or exit explore mode. This is done by means of a meta controller. It's implemented as a non-stationary multi-arm bandit that maximizes episodic returns. I will put a link in the description for the underlying theoretical aspects here, which we will not discuss in this paper, but if you're interested in that, you could have a look. It allows the when of exploration to become adaptive to both the task and the stage of learning. So in other words, you can change your behavior over time, and it can do so in an automatic way without having the need to parameterize that in some sort. The second adaptation that we're introducing is homeostasis, which makes the algorithm robust against variability in trigger signal level. And that's what we can illustrate, or what we are illustrating sort of in the right-hand figure here. The overall approach is that the informed trigger signals, so when we have informed switching, those trigger signals may vary substantially across domains and across time, just as a natural consequence of, for example, the rewards that tend to be present in that sort of part of the environment. And homeostasis adjusts the average, so it's a rolling average over time, in such a way that the trigger signal is always more or less equally likely to get hit over, let's say, medium long-term times of exploration, or just acting from the agent side. So the idea here is that the state space might be more or less likely to actually hit or cause the trigger to be hit. And with this homeostasis adaptation, we keep it more or less robust across the entire domain for getting hit. Otherwise, you might run into scenarios where in some parts of the state space, you pretty much never go into exploration just because you're sort of unlucky in the setup. So that's what we're circumventing here. These two adaptations are important because we can see those reflected in the upcoming results that we're going to have a look at now. So this is a bit more detailed and a bit more complex as well. Let's start by looking at a couple of definitions that we require. First of all, we have the overall exploratory proportion px. This tells us how much on average we're actually in explore mode. We have the length of an exploratory period, nx, so how long this exploration period is, the episode length L, and then a relative summary statistic of exploration, R med x, which is the median exploratory length divided by the episode length. So if this is close to 1, that means every time we go into explore mode, we pretty much stay there for the entire episode length. What we can see in these summary figures here is R med x on the x-axis, which means how long our exploration periods are. Px here is how much time we generally spend on average in exploration compared to exploitation. There's one figure for each game, and we have two slides with, this one for uniform exploration and the other one for informed. And what we can see down here is essentially the performance as well for each of the different models on this particular game that we're considering. So the colors indicate different models, and they are explained down here at the bottom. And before we explain the models, we can also see that we, for each model here, have a square, a line, and then a cross. The square indicates the average point during the first 10% of evaluation, and the X represents the point for this particular model during the final 10% of evaluation. And what changes here is both PX and R med X, and that is a consequence of the bandit adaptation that we discussed in the previous slide. So the bandit has the opportunity to change the characteristics over time, and we can see in all of these examples that it tends to do so. Now, let's look at the models as well. First off here, we have an episode level uniform exploration model. The second one here is a uniform exploration model with a 10 steps exploration length. This one has a 0.001 probability of entering explore mode, given that it's an exploit. It's informed, so the trigger signal is informed, and we start in the greedy mode. For all of these, in fact, we start in greedy mode. Then we have another one, but instead of a fixed probability here, it's informed by the agent. So a probability informed by the agent. The third one here has informed probability both entering and exiting the exploration. This one is also probabilistic and informed by, well, sort of set by the bandit, but it's symmetrical in that entering and exiting gets the same probability. The next one here is similar to the one above, but it's actually a fixed length. So it's not probabilistic, but really, you know, you get a certain amount of steps before you're supposed to switch between one or the other. And the final one here is also a step-based one, but it's, well, first of all, blind as well. And secondly, we have different triggers for entering and exiting. Okay, so that's a description of the models. And we can see here in Frostbite, this is the only game where the informed trigger clearly outperforms the blind equivalent. So we can see in the performance here that the clear winner is the informed trigger one, and the blind equivalent would be the purple example here, and we can see a clear benefit for the informed trigger. That's not the case in general for these games, though. As you can see, the performance indicated down here is not substantially better. I think the clear counterexample is Phoenix here, where we see that the blind equivalent clearly outperforms this informed trigger variant. Okay, in Montezuma's Revenge, which is the game that we can see here, we have the informed symmetric trigger variant with, well, yeah, a clear sort of gain in terms of performance. And this illustrates actually that just the PX is not sufficient to outline how good the performance is going to be. You can see here on the PX characteristic or statistic that the green one is quite similar to the other ones here, but the performance that we can see is clearly different. And so normally in reinforcement learning, let's say papers, PX under, let's say, an epsilon greedy strategy is usually what you would refer to. That's about as much information as you would give, but clearly we can see here that more nuances are useful when it comes to characterizing the exploration, because we have a massive difference here in performance, but really pretty much the same characteristic in terms of, yeah, the amount of time they spend in exploration. And here we can see that only the blind doubly adaptive model escapes the local optimum of Phoenix. So there's a local optimum of Phoenix, and the only one that actually is able to break that is the purple one here. And also the bandits here in this game radically shift the statistics over time. That's indicated by the long lines here. If we move over to the informed intrinsic, or to the, sorry, the intrinsic reward exploration, we see exactly the same figures, or exactly the same games and the exact same illustrations, but what we can read is a bit different. As we said before, PX is further indicated here that it's not a sufficient statistic to describe how well performance is going to be. We see another example of that here, where we have quite substantial variance in terms of performance, but a similar PX for all of these models here. Also, the bandit adaptation shifts the statistics into different directions for different games. So it's not just that they all get adjusted, but depending on the game, you would adjust in different directions sometimes. So you can see here, for example, we go upwards and to the left, or sorry, since we start here, we go down to the right. And here we can see, I mean, clearly the opposite direction almost, or a clear preference for going left or reducing our medx in this case. So it's not clear that we always go in one direction as we improve the performance of the agent, or as we converge towards some sort of solution for our agent. A common pattern, however, is that PX needs to be far below 0.5 in order for us to have high performance. So that's sort of aligned with some of the common findings in reinforcement learning, that you want to reduce the amount of exploration as your agent becomes more well, proficient or better at navigating the environment. Lastly, what we want to explore and what they investigated in the paper is the starting mode. So we discussed this in the beginning, that you can start either in explore or exploit mode, and whichever one of those you choose will have significant impacts on, potentially have significant impacts on the final performance. That's what they're investigating here. We can see a comparison between starting in the greedy mode, so the blue shaded line here, or starting in explore mode for intrinsic informed or for uniform exploration mode. And for both of these, we can see that it varies between games, which one is the better. Specifically, I mean, for Frostbite, if we take that for an example, we can see a clear preference for starting in the greedy mode as opposed to starting in the explore mode. But we also see counterexamples here, for example. So it depends on the game, and the reasons are those that we outlined in the beginning, that sometimes the starting states could have a very significant impact on which options are available to you later. And if that's the case, then it probably makes sense to start exploring, as your starting state, because then you could potentially learn those moves early on. Whereas if you would start an exploit, you might take the wrong action early, and then it doesn't really matter if you explore, because your performance is still going to be poor because you already messed up, let's say, the future, your future prospects of getting any reward. So depending on the game, we see a differentiation there. And that takes us to concluding the results that were found in this paper. So for exploration, there seems to be an optimum in terms of temporal granularity, and intra-episodic exploration is the right step toward finding that. They also find that the raw amount of exploration px is not a sufficient predictor of performance, implying that the temporal structure matters. And this is perhaps an indication for future reinforcement learning research to be more sophisticated in terms of the exploration methods that they adapt and look at more than just the overall fraction of time spent in exploration. It seems that reducing px far below 0.5 is necessary for high performance. And this is something they find for both the uniform and intrinsically informed exploration modes. Despite those having very different performance overall for certain types of games, that seems to be a common finding. And lastly, prolonged intrinsic exploration seems more useful than prolonged randomness. So if you're increasing the time period in which you explore, then it becomes more necessary to have some sort of, to be informed of the way you explore. I think that makes sense intuitively as well, if you think about it, that if you are exploring for a long time, just taking random actions might not actually lead you somewhere. But if you, during that prolonged period of time, explore the states that you are most uncertain about, you might be able to find new information. Those are the conclusions of this paper. I think it's very interesting, and hopefully we can make some videos going forward about, that get into more of the details on these sub-problems, really, because this is taking a first stab at this very big problem, and I think it needs to be addressed bit by bit to get some more clarity on what is appropriate when it comes to these hyperparameters and different adaptations that we can make. That's where we're going to end it for now. So thank you all for watching, and I look forward to seeing you in the next video.